So good afternoon. Welcome back again. And we'll now continue. Tim Hobbs will give us the first of two lectures. So Tim, good to have you here.
Yeah, thanks so much, Fred. I'm really delighted to be here with all of you. Hope it's been an exciting and a fun meeting. Hopefully I can tell you some new things. So let me just first introduce myself. I'm Tim Hobbs. I'm a staff scientist at Argonne National Lab. I'm a theorist in the high energy physics division, which might make me a little atypical relative to some of the other lectures at this summer school. My aspiration is to tell you a little bit, hopefully things you've already heard, but some new things as well, perhaps from a new perspective. Before I begin, just for my own curiosity, I sort of expect I know the answer, but how many of you would identify yourselves as nuclear physicists? And how many, well, okay, great. How many would say they're in high energy physics?
Both.
Fabulous. Okay, or in both. Yeah, some might be, somehow. I kind of identify with that, actually. I have interests that cut both directions too. So that's great. It's a fairly even mix. So what I've been tasked with doing is telling you about, obviously, the EIC. Pardon me if I struggle with this device because I've never quite done this. The EIC, of course, like the other speakers, really the perspective from high energy physics and in some sense leaning on the parton distribution functions as kind of a vehicle to tell you this story. And I think it's interesting to do so because the PDFs actually, I think, transcend, if you can call it, the divide between particle and nuclear physics in a really interesting and subtle, really interesting way in a number of subtle ways. So I'll hope to sort of tell you a little bit about that. Please feel free to interrupt if you have questions along the way. So I think a lot of what I'll say, you may have heard some version of perhaps in the first few days of this meeting. I believe you've heard a little bit about parton distribution functions already, the PDFs. For that reason, I'm going to go ahead and begin by actually asking an important question to motivate what we'll be talking about. And that question is, you've heard a little bit about PDFs. I think you have some conception of what they are, basically. How do we measure the PDFs? Does anyone want to venture a guess or some sort of answer? How are the PDFs measured? Anyone brave to try? Yeah, go ahead.
Well, my understanding is that it was an accumulation of results from the deep inelastic scattering experiments at Hera.
Yeah, that's a very thoughtful answer. I noticed you had your hand raised too.
Yeah, well, can't really say that we measure them because we kind of fit theoretical predictions to the data and kind of assumes, we have some replicas. Right. Yeah, that's so. I mean, I think you're both thinking in the right direction. You're a little bit more along the lines of what I wanted to say. So I beg your pardon that I've asked you essentially a kind of trick question just to maybe get you thinking in this way. What I wanted to say, or what at least I had in mind to say, is, I mean, the PDFs actually are never measured using this language. At least people often say this. In fact, very esteemed physicists even say that we'll measure such and such PDFs. That's sort of nonsense, actually. They're never measured. And the fact that they're never measured actually is intimately tied up with the fact that we have confinement in nature. You never actually observe quarks. And so the PDFs are essentially theoretical objects, right? They're somehow inferred, right, from data, or perhaps in better words, they're extracted essentially in a grand inverse problem. Essentially, that's what this gentleman was just saying. And so if you get nothing else from this meeting, at least from my contribution to it, one thing that I would really ask in your future career, whatever you do not ever create plots that look something like this. And this is actually not uncommon. And both theorists and experimentalists are guilty of this. And I don't take an example so that I don't hurt anyone's feelings. But what people will often do is they'll plot a PDF, or in this case, maybe something like a ratio of PDFs, and claim that there's some measurement that actually allows you to unfold this directly, and might even plot data essentially with an uncertainty for the PDFs. So that cannot be done. That should never, don't ever do that. Don't ever do that. So again, as I was just trying to say, you have to in fact infer these things from high energy data. And the process of doing so has a very long history that really goes back to the early days of QCD.
You already answered this, Tim, but like when you provide cross sections like in the EMC effect and you set things up properly, can't you have everything cancel? And, oh no, that's a ratio of F2s, not F1 over F2.
Yeah, so yeah, thanks for asking that question. So what I was trying to say here, these are both meant to be PDFs. So this might be something like D bar over U bar or D over U, the actual PDFs, not, and what you just said is fine. Of course, I can have a ratio of Drell-Yan cross sections or structure functions or things that are empirically observable, no problem. What you can't do is directly measure a PDF or something derived from the PDFs, like a PDF ratio. That's a no-no. Any other questions on this conceptual point? So I wanted to tell you both how we actually go about doing this, but first give you a little bit of a historical context. I mean, where we rest in this field follows an accretion of many intellectual developments, of course. And I think you've heard a little bit about this. Many of you might have a nuclear physics background, so you might even know really sort of non-trivially about some of these types of things. I mean, the evidence, the fact that the proton is not a fundamental particle. Really, we've been aware of this for actually quite a number of decades, going back to the 1950s. And arguably what was most responsible for this was measurements of things like, not the PDFs, that came later, but actually form factors, for instance, of the proton. The idea being that you perform an elastic measurement, maybe an electron scattering from a proton where you then observe an electron, a recoiling electron and proton in a final state. And basically you measure the probability, that's what's encoded in the form factor, for you to actually find that final state proton, for it to essentially remain intact and not disintegrate in the final state. What we found, or what Hofstadter found actually in the 1950s in experiments at SLAC, was that the form factor actually fell off much more rapidly than would have been expected if it were truly corresponding to a fundamental or non-trivial point-like particle. That hints at the fact that the proton has some sort of substructure. It's, if you'd like, sort of squishy. That's one thing. Another thing, of course, is that our predecessors found a sort of particle zoo, if you'd like, of many different types of hadrons that could be organized according to some underlying symmetry, things like hypercharge or strangeness, or just electromagnetic charge for that matter, which hinted at the fact that there's something inside these bound states that could be somehow rearranged in some way to give rise to these various states. That goes way back. Following that, of course, in the 1960s, still more pioneering experiments at SLAC, for instance, revealed some of the details of that internal structure inside the proton. And in that case, the way that's done, as I think many of you appreciate, perhaps from some of the former lectures in this meeting, was through inelastic scattering, where you no longer actually recover the proton in the final state, but really just pay attention to the final state scattered lepton, the electron in this case. And what was found in these measurements, of course, is that you don't have this indefinite decay of these types of cross sections that you'd measure, but in fact, a stabilization and an approximate scale independence. There is a little bit of scaling, which was called Bjorken scaling. It is consistent with the fact that the external probe basically resolves now some essentially point-like looking objects inside the proton, which were ultimately identified as being the so-called partons. They look like dense point-like charges, and those are the quarks, roughly speaking, as identified by Bjorken and Feynman, and ultimately Gelman as well. How exactly is this done? I think many of you know it's done through deeply inelastic scattering. And the idea is that in DIS, you have a very clean process that allows you to access the quark substructure of the proton. And what you do essentially is you take some external probe, of course, an electron or some electroweak gauge boson that interacts via exchange from the electron and the proton, and that essentially resolves the quark-like structure inside the proton. What that amounts to doing is actually telling you something about this hadronic blob in a representative cross-section that can be unpacked in terms of electroweak structure functions that you all know and love, which in turn, at least at leading order, have well-known expressions of parton distribution functions that scale, as I just explained a moment ago, in terms of a momentum fraction x, and they have essentially a kind of energy scale Q, a scale inside this. So that's interactions at the quark level. What crucially happens, of course, is that you can measure this DIS cross-section at many different exchange virtualities or at many different momenta of the exchange photon. And there is, as I'll explain a little bit more detail later in this talk, we can basically, through theoretical machinery, relate these structure functions at different scales according to our knowledge of radiative effects, where quark lines essentially radiate gluons, and that is what governs the sort of the scaling from, the evolution from one scale to a higher scale. And so for that reason, what's really crucial is to have data at many different scales to constrain the gluon content as well. That's roughly speaking, of course, how this works. And through doing this, what has been learned over the intervening decades really is the fact that the structure of the proton is incredibly non-trivial. I think that's why so many of you are, of course, here and eager to learn about this. The proton does not look like its sort of leading bound state valence-like structure of just three light quarks, UU and a D, that would be responsible, of course, for giving rise at high values of the momentum fraction in the PDFs to something that looks valence-like, which is to say that it peaks at a momentum fraction of something like a third, as you would expect for sort of like a Fock state picture where you're dominated by one of sort of three valence-like quarks. But instead, you have this growth at low X due to the presence of a C that's generated, again, radiatively through gluon emission, as I was just saying. And for that reason, there are contributions to the structure of the proton, particularly at higher scales, not just from up and down quarks, but from really a whole collection of many other flavors. And I'll explain a little bit more how that works, roughly speaking. How exactly do we get at any of this information? And what's sort of the crucial aspect of QCD as a quantum field theory that really lets us do this? Well, it's the fact that, put formally, the beta function of QCD is, as we would say, negative definite, which is to say that as I increase the momentum scale in some hard interaction, basically the strength of the effective quark-gluon interaction becomes perturbatively smaller as I go to higher and higher energies or higher and higher momenta. And what that does is it allows me to delineate basically two different sort of scales in any sort of calculation that I might do for a cross section or a structure function. I can think of contributions to that process as coming from short distance interactions that in the QCD factorization language, I can use basically my knowledge of QCD perturbation theory to calculate things in that case, and then interactions at sort of lower energies that are non-perturbative. And it's there that I wish to actually parameterize and ultimately extract the parton distribution functions by fitting the data that I might have at my disposal. Now, a fundamental question, which again, I think really motivates so many of you in this room is, how exactly is it that QCD we can calculate very well at high energies in perturbation theory? How does that same theory, when I scale down to low momenta, how exactly does that same basic theory really give rise to, if you'd like, the emergent properties that I observe in bound states like the proton or other states for that matter? That's really a fundamental issue that motivates so many of us that work in this field. And what's particularly interesting, I think, about the parton distribution functions is that a lot of the physics that is responsible for answering that question is somehow inscribed on the PDFs and the detailed aspects of their behavior. Now, the way we actually do this, as I'll get to a little bit later in this talk, is through what we call a QCD global analysis. Is anybody in this room, have any of you actually been involved in any of this? Fitting PDFs, or for that matter, related things, related quantum correlation functions like TMDs. Okay, good. So I'm seeing a couple of you. So that's excellent. The sort of theoretical technology that I just described, QCD factorization. What we do is we basically mechanize that into performing these very large scale PDF fits. And what we're really doing is we're extracting some sort of hadronic matrix element that's constructed from quark level fields of relevant operators. And for something like a collinear unpolarized PDF that we care about so much for LHC physics, for example, it really looks like a matrix element of the gamma plus operator. What's tricky about this is the fact that there's really, despite the comments by my colleague Wei Wen that you heard about last week, it remains extremely non-trivial, depending on how you wish to think about it, to practically impossible at the current time to really compute these types of matrix elements from first principles in QCD. We're having developments that are going in the right direction to make that more and more of a possibility. And so lacking that for the current time, what we do phenomenologically is we instead fit some very flexible parameterization at a suitable boundary condition, basically for QCD evolution. And I'll explain how that works in just a moment. And then in principle, if you have a very flexible such parameterization and you understand perturbative evolution well enough, then you just simply try to fit the world's data phenomenologically. That's basically the idea. If you want this to work, then what you really need is a diversity of data from many different scales and many different processes. Now, I can ask you in a more practical sense, where exactly do you get the PDFs? How do you find them? Well, you just go to LHA PDF, as I suspect many of you have done, and you download them. Okay, have any of you done this? Have any of you used LHA PDF? Show of hands. So some of you. So this is a useful skill to have, no matter what you do, theorist or experimentalist. If you do any sort of phenomenological calculation, or you care about generating events where you have colliding hadrons of some sort, then in general you'll need this. So the PDFs are in fact available in the LHA PDF repository on HepForge, for instance. There are a lot of handy wrappers, including for Julia, that work also with Python. So as I said, no phenomenologist should leave home without having some knowledge of how to do this sort of thing, for instance. And so basically, whenever people like my colleagues and I, or others who work in this field, release a global fit, then in general, we publish them to LHA PDF, and there are many hundreds of different fits that can be used for phenomenological studies. And you can essentially go on your merry way, actually computing things in this fashion. More fundamentally, however, which is probably what you all care about, how exactly do you extract the PDFs? Wondering if I can get rid of this. It's a bit of use.
Yeah, there's a stick. Everybody uses, oh, that thing. 3 dots on the right. Side floaters.
Okay, so great. Are there any questions up to this? Does it sound familiar to what you've heard already, perhaps in this meeting? Good. Yeah, so as I just mentioned, we need a lot of data if we do this. And the reason for that is because we have to somehow extract this complicated X dependence for the PDFs. There's a flavor dependence, as I'll go into a little bit more detail in just a moment. And so this is a sort of a representative plot, basically, of the data that go into a typical such global fit. So this is an analysis that my colleagues and I released a couple of years ago. This is inside the CTEQ global analysis group, CT18, which was a very large scale analysis targeted principally at physics at the Large Hadron Collider. And what this plot shows basically is all of the data that we fit to inform the CT18 global PDFs represented in a space of X, where X is of course the parton momentum fraction, and this momentum or energy scale Q. And what you can see in the plot like this is that there are several dominant blocks, if you'd like. So the LHC data, including some data also from the Tevatron, can be seen, of course, at the higher energies. We have very important contingents, of course, from Hera as well, informing particularly the low X structure of the proton. And then very important too, somewhat at higher X and lower momenta, is this block of many different experiments from fixed target sources that are somewhat older data, but nonetheless very constraining. So the question is, if I have all of this information from experiments, how exactly do I really try to extract the PDFs from them? That's what I'll get to in just a moment. So a modern global analysis emerges from a fit of all of this hadronic data, as I just mentioned a moment ago. At least for high energy physics targeted global fits, the sort of working standard in this area is now next to leading order in the strong interaction. And increasingly, we're even looking at an order beyond that, N3LO as well. What I want to really stress to you all is the fact that it's a very complicated endeavor to try to actually extract these things from all of the data that we have. It involves this very subtle interplay of perturbative theory, as I was sort of hinting at a little bit earlier. It involves a great deal in terms of just sort of computational aspects, And then a subtlety that I wish to give you some flavor for is the fact that fairly complicated statistical theory comes into play as well. So the idea is once I have all of that, I can of course fit the PDFs, not just central values, but crucially with some uncertainty as well. And this gives, at least in this case, some sense for sort of the collinear, that is to say the one-dimensional structure of the proton. So I'll go into this in just a little bit more detail in a moment. Now, why do we care about this? I already kind of suggested already that we care about it in part because QCD is interesting and we want to understand QCD as a theory and its implications for nucleon structure in more detail. There's also a practical side of this question as well, which is to say that high energy physics experiments, for instance, like those at the Large Hadron Collider, of course, depend very, very importantly on the PDFs. Why is that? Of course, it's the case because the LHC collides protons with other protons. And if you want to, for instance, do Higgs physics to higher and higher precision, then you need very accurate determinations of these PDFs. And as I just said, they depend, the calculations, for instance, for some production cross-section, maybe some electroweak process at the LHC, depends on my knowledge of both the perturbatively improvable hard interaction as well as the information that goes into the non-perturbative stuff in the form of the PDFs. And I'll go into this in a little bit more detail tomorrow, how all of this translates into high energy physics, of course. But it's very important really across the board in terms of limitations to, say, Higgs physics or electroweak processes, or if you'd like, processes in the QCD sector that might be sensitive to physics beyond the standard model, like TT bar or jet production. And the name of the game in this area, as I'll explain in a little bit more detail tomorrow, is, of course, I want to be able to calculate the standard model expectations for all of these different processes, in this case relevant, for instance, for Higgs production, and observe the detailed couplings of the Higgs to other standard model particles with ever and ever greater precision. And it turns out that actually the PDF limitations are really crucial in sort of the name of the game of getting things better. Are there any questions about any of this? Please feel free to interrupt and ask. Yes.
I have one quick question on the previous slide.
Yeah.
Why is the charm PDF so much more constrained than something like Strange?
That's a great question. I'll get to that in a little bit more detail, but I will give you a quick answer. That has to do with the fact that in a fit like CT18, the charm PDF is generated entirely perturbatively. So it's essentially generated just from gluon splitting, where so the gluon goes to a CC bar pair, which is why, especially starting, we parameterize our PDFs essentially at the charm mass, which is something like 1.3 GeV. So this is after a very small interval of evolution. And this is plotted with respect to X on a logarithmic scale. So what you'll note is that the charm PDF is practically zero until I get to very, very low X. And that's because this shape is really being driven by essentially convolution of splitting functions. With the gluon, it takes off at very low X. But in general, what's done, at least in a fit like this, is the charm PDF exactly at the partonic threshold is set exactly equal to zero, and then it's generated. So that corresponds to a very small uncertainty. It's not freely fitted. Any other questions? Yeah.
What does geoverify mean? This might be a stupid question.
Yeah, no. That's not at all. That's probably an indictment of the notation. So the gluon grows sufficiently quickly that it doesn't take long for it to be sort of off the charts. So it's just a factor of 5, just to sort of put it in the same ballpark. That's yes.
And then for the charm, there's the addition of the intrinsic charm that comes from 2 gluons as opposed to 1 gluon splitting that peaks at X of 0.4.
Yeah.
Maybe was seen last year at the LHC. Is that in the code or no?
So this calculation, and maybe you induce me to talk about this a little bit more tomorrow. This particular fit assumes a purely perturbative charm only. You can do other things. So
The same thing should happen to Strange too.
Well, so I think there's less ambiguity in the case of the Strange content, that there really is some non-perturbative mechanism that generates it already at some very low scale. So Strange is in general always parameterized with some non-trivial form and fitted to the available data, not the charm though, typically. Any other questions? Yeah.
I noticed that in the very small x, there is a decrease for the gluon distribution, right? Does it coming from the gluon saturation, something like that?
So I mean, yeah, again, the gluon, again, we're at some very low scale. So initially the gluon is just parameterized with some non-trivial fitting form. If the gluon evolves extremely rapidly because it's coupled to, of course, the quark degrees of freedom as well as to itself, because it's a non-abelian gauge theory. So we fit the gluon according to whatever the data seem to prefer. And this particular shape at very low X is just a reflection of the non-perturbative nature. Note that the uncertainty is extremely large. So at some point, if you continue plotting logarithmically down to smaller and smaller X, you'll get some huge takeoff because there are essentially no data that are sensitive to that very, very low X behavior. Since you asked, I'll also note that the behavior at really low X, particularly for the gluon is really, I think, a frontier in this area, exactly how you treat physics effects at low X, whether or not in terms of the perturbative calculation, there's some sort of effect that, mandates like a low X resummation. These kinds of things are very active. Any other questions?
What about B quarks?
Yeah, so the B quarks, you all are sort of anticipating what I'll get to a little bit later. At this particular scale, so this is Q of 2 GeV, I don't yet have an active bottom quark, but of course, as I evolve to higher and higher scales, and in fact, you'll see this a little bit later, then of course I can perturbatively generate the B quark. I would do so at the appropriate threshold in exactly the same way as the charm. And so it would have a very, very similar shape that's essentially generated by evolution effects and very closely correlated to the. So it's not on this plot, you'll see it a little later. Any other questions? Okay, I'm going to keep on keeping on in that case. So I tried to convince you that we care about this as high energy particle physicists. At least if we want to do very precision phenomenology, we have to know the PDFs very well. What I want to mention very quickly, and I'll sort of march through these results in just a couple of minutes, basically. But again, the PDFs are fundamental, not just in that practical sense, but in the sense that they're also very closely bound up with our understanding of QCD. And that's, of course, really the name of the game as far as the electron-ion collider. It has all of these various banner motivations that are not quite high energy physics motivations necessarily, but they're interesting from the perspective of QCD nonetheless. And those pertain to things like, do we understand how hadronic bound states obtain their mass, at least in a detailed way? Do we understand that? Is there some non-trivial breaking in terms of the flavor structure of the proton or of other states? For instance, SEQ symmetry violation, or is there something non-trivial going on in terms of the strange or even the charm content? How exactly does one come up with the spin of the proton? And similarly, are there analogs of this in terms of interesting things happening in the nuclear medium? These are all questions that are really, the EIC is actually targeted to answer these sorts of things. And of course, that's why, as you all are here, there's a great deal of enthusiasm and things continue moving right along. So just to very quickly give you a sense for these things, why do you weigh something rather than nothing? It's because you're made of baryonic matter, of course. That I delight in telling my fellow my fellow high energy physicists that the Higgs mechanism is not chiefly responsible for the mass, at least of the visible universe. And that's because there is, whenever you're talking about, for instance, quarks at very low energy, they're dressed by some non-perturbative, complicated interactions that convey mass, that weigh something effectively. And more formally, that's to say that there's basically a QCD gap equation, for instance, that's relevant for the strong interaction. And it just so happens that if you decompose the mass, for instance, of the proton, there are so-called kinetic contributions that relate very closely to the knowledge of the moments, for instance, of the unpolarized PDFs. That's with respect to the mass. There are questions in terms of how flavor symmetry might be broken inside the proton. So the oldest analyses in general assumed that U bar and D bar and strange and anti-strange for that matter were all essentially exactly the same. And you could basically rotate according to some flavor symmetry from one to the other. But while that may well be the case at very high energies, we expect that The very same non-perturbative interactions that give rise to the nature of the proton as a bound state could actually break that sort of flavor symmetry. And that could, for instance, have consequences for the violation of the equality between the anti-down and anti-U distributions, for instance. In that case, actually, some sort of coupling to the pion, the proton to the pion, can actually break that. And there are measurements that in principle are sensitive to that behavior that are very interesting to us. The strangeness, as was asked about just a moment ago, there are actually a lot of elastic measurements that some of you, especially maybe on the nuclear side of the fence, might be aware of. But we could ask the question, for instance, are there PDF sensitive experiments, for instance, in deeply inelastic scattering that might be sensitive to the strange content in the proton? In general, we're finding it very difficult to unvary that information at the level of elastic form factors that I mentioned a little bit earlier. You could do the same thing for, was there a question? I'm sorry. You could do the exact same thing for charm in principle, as was actually just asked a moment ago. Is there some sort of non-perturbative charm that isn't generated purely through radiative effects, as I was saying a little bit earlier? It remains an open question. It's a question that ultimately comes down to selections of models and whether we have data with sufficient discriminating power to actually answer that question. And I might say a little bit more about this actually tomorrow. And again, what I want to really stress is that the subject of uncertainty quantification in the PDS, so saying that I have data, I know how strongly they pull on the fitted PDS, is really crucial to making some sense of this question. There's, of course, the origin of spin, which I think many of you heard about, which has exactly an analog to these kinds of questions that I'm talking about in terms of the collinear unpolarized PDS, where one can play the same sort of game, basically, and try to construct, by appropriately summing and integrating over spin-dependent analogous PDFs, the total spin 1/2 of the proton. That remains very problematic to this day. And then lastly, you can, of course, think about the partonic structure, not of hadrons, but of nuclei, including of heavy nuclei, and ask the very non-trivial question, what exactly happens to a nucleon once you put it inside the nuclear medium, once it's found inside of a nucleus? And you may ask yourself this question. I would argue no one really knows definitively. Does literally nothing happen? Does a nucleus basically just look like a bag of marbles of many nucleons jumbled together? Does the nucleon basically sort of melt, if you'd like, or dissolve inside the nuclear medium? Are there some sort of other things that happen? Are there correlations between things that still look baryon-like inside the nuclear medium? These are all really interesting questions. And in fact, you can do basically the exact sorts of things that I'll talk about in this talk, focusing on the proton for nuclei and parametrized PDFs in that case as well. So there are all these different types of things that we wish to understand and answer. Are there any questions, by the way, before I move on to a slightly different phase of the talk? So we would like to actually answer those questions that I just sort of posed by analyzing and extracting the PDFs. How exactly do you do it? I gave you a little bit of a hint of how this works, of course. And as I mentioned before, the crucial thing is really QCD factorization that allows you to extract these types of matrix elements. And really the essential thing, for instance, is if I want to write down, say, some Drell-Yan cross-section that I might measure at the Large Hadron Collider, this is just a charge neutral Drell-Yan production process, then I can write down that cross-section in a QCD factorization theorem that is valid to all orders. And really what becomes, my mission in doing these types of calculations is how well can I calculate at a given fixed order this hard interaction kernel that then allows me to parameterize and extract the PDFs in this case, where now I'm actually carrying out a convolution between some perturbatively calculable hard coefficient that I can write down in terms of basically Feynman diagrams, and that has the appropriate factorization and regularization scales entering it, and then the PDFs, which similarly depend on this momentum fraction in this case because there's a convolution psi, and then again, a factorization scale. And throughout the rest of this talk, these factorization scales are exactly the same as the regularization scale. And you could use whatever regularization prescription you care to, for instance, MS bar, when you go about this. I would also point out that there are power suppressed corrections that essentially break this factorization theorem that you'll note are especially relevant as I go down to sort of lighter and lighter scales, and control over those. And especially those of you sort of EIC enthusiasts, nuclear physicists, these will really interest you because in fact, they can potentially sort of spoil the validity of this factorization theorem. So controlling them is quite essential. How exactly does all this work and why do we use this sort of technology? We do it because when we write down a factorization theorem of this type, what we find is if you do the calculation at a given fixed order and then go up to higher and higher scales, what you find crossing partonic thresholds is you get logarithmic corrections basically that become uncontrolled as you go to very large scales. And the idea is that you basically resum these effects by absorbing them into PDFs as you cross each sort of mass threshold from say a 3 flavor scheme up to a 4 flavor scheme actively involving the charm PDF. There's an additional subtlety with this, which is the question of how exactly do you really do these calculations for a specific measurement? And the idea, of course, is that I can match basically the kinematics that appear externally in an experiment. For instance, something like the virtuality that I would infer from a DIS measurement and X Bjorken, which I can construct from external kinematics. I can match those sorts of things to the partonic level physics that enter the factorization theorem that I just wrote down. And you do the same thing for different processes. That's DIS. For hadro production processes, for instance, at the LHC, then you have similar matchings between momentum scales that enter the problem, might be a PT or an invariant mass, or a rapidity, for instance, going in the direction of the momentum fraction. What one has to grapple with, however, is that these types of matchings, which I show on the screen at the moment, are sort of born level matchings. And there is an inherent scale uncertainty to how one does this. That's actually a theoretical uncertainty that has to be controlled in doing these types of things. That's roughly speaking kind of the main idea of doing these fits. I mentioned a little bit earlier the fact that there is this complicated sort of scale dependence that has to be actually calculated. And we can calculate that based on our knowledge of QCD as a perturbative theory. So in practice, of course, when you go to actually fitting data, you fit data that live at many different kinematic scales, as I just showed on the previous transparency where I match them. What I ultimately want to be able to do is to understand the scale dependence of the PDFs, for instance, where this F sub IP refers to any flavor inside the proton. And if I want to evolve up to a higher scale, then I have to understand a splitting function, which diagrammatically has some sort of interpretation, for instance, where a chloride might radiate a gluon. And there are other such diagrams at leading order where now a gluon can split to QQ bar, as perhaps many of you have seen. And that just gets convoluted with the PDF of a given flavor that's appropriate for this sort of diagram at the relevant scale. And so I can actually just go on my merry way. I can calculate each of these splitting functions. In general, they're known up to alpha cubed, for instance, at least in terms of practical calculations for PDF fits. Now, I think as some of you mentioned, what all of this leads to is this very interesting and subtle behavior in terms of the fitted PDFs that you would ultimately extract from the hadronic data. So this is again showing that plot that inspired various questions a little bit earlier in the talk at a low scale just above the fitting scale or the parameterization scale, if you'd like, at 2 GeV. And what you see at this low scale, where I'm now plotting the up and down quarks and then the various anti-quark distributions, is that the shapes are very much dominated by these peaks that occur, roughly speaking, around x of a third. And they're therefore very much sort of valence dominated. And I also want to stress that, especially if you look, for instance, at things like the strangeness or the anti-quark distributions, there is this sort of subtle dependence on X that doesn't look exactly sort of like this straightforward sort of takeoff or singular behavior at low X, which implies that there is indeed non-perturbative physics that governs those parameterizations or those shapes. And what one finds is that in general, what perturbative evolution does is it effectively sort of shifts these features of the PDFs that occur at high X down to lower X. And that can be seen when I go to a much higher scale, for instance, Q of something like 100 GeV. And I can sort of just dance between these two panels to illustrate roughly what happens. You can do this on your own time as well with the slides that have been uploaded. And you can see essentially what I just said in words, the fact that the up and down PDFs sort of bleed away down to very low X, and the valence-like shapes increasingly are sort of swamped by the effects just of the perturbative evolution. The charm and bottom PDFs, which are generated entirely radiatively, very closely track the shape of the gluon PDF, as is now evident as I go to this higher scale. And since I'm now at a sufficiently high scale, you can see that the bottom PDF, shown in sort of brown, is also now present. What you could also notice if you look at this slide very closely is the fact that I can clearly see that it's quite challenging in general, especially as I go to lower X, if I want to actually separate and have some understanding of the flavor dependence of the PDFs and try to actually distinguish, for instance, the strange from the lighter quark C, that is the anti-up and down PDFs. It's very, very tricky to actually try to do. Yes.
I have a question about the charm in the bottom.
Okay.
Like if they come from not radiated, not from gluon splitting, but from like two gluons, the intrinsic charm idea.
Yeah.
That seems to me very perturbative. How is that not perturbative?
Because so that sort of mechanism, you ask a very subtle question that maybe I would like to go into a little bit more detail tomorrow. I mean, the idea is that you have that sort of physics somehow present and contributing to the proton structure at a very low scale, where you still have very strong coupling, basically. You have these multiple attachments between the heavy quarks and the rest of the valence structure. So you do have these types of diagrams, but the idea is that they generate something that looks sort of valence-like, and that is not just pure regular extrinsic evolution that has the sort of typical shape. Ultimately, it gets rather subtle and ambiguous because you ultimately want to map that sort of physics that you just described to some kind of model, and how that is implemented in a systematic way in a sort of factorization theorem-based approach like this is not really clearly understood, I would argue. I can talk about it a little bit more tomorrow. Now, what I wanted to mention is some of what's going on can be understood just by decomposing this representation of the PDFs into separated sort of valence and C distributions, basically, using the logic that, for instance, the up PDF basically is just a straight linear combination of the valence, which is to say the U minus U bar PDF, and something that's C-like, which is basically just the anti-up PDF. And so if I were to plot, this is one of our sister groups, the MSHT group, and their recent release of PDFs. If you plot, for instance, all of the PDFs again at a sort of lowish scale, it's not unlike what I was showing a little bit earlier, the valence structure is very evident for U and D, for instance, marked by the fact that these vanish as one goes to very low X, and you get this very clear sort of hump-like structure at very high X, again, peaked around X of a third or so. As I evolve to higher scales, actually what happens due to the fact that you construct these valence PDFs from sort of U minus anti-U, the C contribution actually roughly vanishes in the difference. So the valence largely persists. But if I combine with the others, what seems to happen is that the valence ultimately ends up getting swamped sort of by the purely C-like the C-like contributions. Are there any questions? Okay, just shout if you have something. So that's kind of a rough feel for how the PDFs are behaving in general in this case. Something I wanted to at least, this would be its own talk basically, but what I wanted to, again, give you some at least idea for is, again, the sense that there are not non-perturbative, but perturbative contributions from heavy quarks that are a very important subtlety actually in terms of doing these fits. And that's due to the fact that QCD analyses like the type I'm discussing end up actually crossing over many different scales. They go from sort of proton sort of scale GeV all the way up to TeV scale physics for the Large Hadron Collider. And so what that means is that as I think about something like, say, deeply inelastic scattering over many different scales, naturally the heavy quark mass basically introduces an effective additional scale into the problem. And dealing with that in the context of QCD factorization up to higher and higher orders gets really, really hairy. It can be dealt with, but typically what you have to do is have some sort of variable flavor number scheme where you fit the PDFs. And as you cross over each partonic threshold, you essentially bump up the number of active flavors. And where it's tricky is the fact that if I use a fixed flavor number scheme where I'm not sort of actively adjusting the number of active flavors as I sort of go up to higher and higher scales, the heavy quarks can again introduce, as I kind of alluded a little bit earlier, these large logs that really spoil the behavior of the calculation. And again, they have to be resummed in some way. So in fact, what's done is that we use a type of interpolation scheme. There are various scheme dependent ways of doing this. So we have one of the creators of one of the very commonly used ones at the back of the room at the moment. And where it's tricky, of course, is if I'm doing this calculation at a given fixed order and fixing the number of flavors, things might work quite well at low scales, but then as I go up to higher scales, then I have problems. And so I have to resum. So the type of interpolation schemes that are used basically implement some sort of subtraction such that when I'm at low scales, then something that looks sort of fixed flavor number scheme like is applicable, and that at higher scales, I adjust up to a higher number of active flavors and things look more massless since I'm at a sufficiently high scale relative to the now sort of smallish heavy quark mass at those scales. So it's very tricky to do this. If there are questions, please ask me about that, or we could discuss it during the discussion. So with that, I come to kind of the last phase of my talk. We'll see how far I get, because I'll try to keep it to the hour to leave time for other questions or just to respect your time, and as well as the talk that's coming later. I mentioned this before, the fact that now that you've gotten some understanding for how the PDF fits kind of work, at least in a kind of half-hour sketch. Again, as I mentioned, what you want to do is now parameterize the physics that you don't know as encoded by the PDFs at a starting scale. And the idea is that I need parametric flexibility in doing that. And what's typically done is one, at least in a fit of the style of CTEQ or MSHT or many of these others, is you write down a form that has some sort of prefactor that vanishes at small x and very high x, that is at x of 0 and 1. And in between, you would parameterize the additional non-trivial x dependence with some sort of multi-parameter polynomial, for instance, that can just do whatever the heck you want. And the idea is that I need many of these different fitting parameters, and I would write down unique parameterizations in principle for each of the various flavors, for the gluon, for U bar, D bar. And there are various ways of doing this actually, and that's an important source of uncertainty. How much flexibility is needed? How much flexibility is needed? You might ask, do I want 100 parameters? Do I want 1,000 parameters? Should I put 1,000 parameters in my global fit? Does anyone see a problem with doing that? Why can't I? Could I put 1,000,000 parameters?
We will have nothing.
Yeah, well, you can try. Yeah, I invite you to do that. The problem is I have to still fit this thing in the end. So I need, a typical fit, as I showed, a little bit earlier in the talk, in kind of that plot showing all the dots, has maybe 4,000 or 5,000 data points from all the information that we have that might be PDF sensitive. So if I wanted to constrain 1,000,000 parameters with 5,000 points of data, why can't I do that? Yeah,
It's like very under-constrained.
exactly. Yeah, I have 1,000,000 unknowns and 5,000 points of information. I can't do it. So there's this kind of interplay between over and under fitting that's very tricky. So in fact, this is an empirical question, how much flexibility is needed in a fit of this type. So in sort of recent years, and it's an open question, of course, how sensitive the data are. I mean, inside the fits that I've shown you so far, S and S bar are actually exactly the same, because We don't have confidence that we have enough data to really distinguish the strange and anti-strange distributions. Maybe we do. It's an active question. What it all boils down to is maybe something on the order of maybe 30 parameters that that control the behavior of all of the various PDFs that we fit. This is an approach that depends on actually having an explicit parameterization of this form. There are other ways of doing it. Our colleagues inside, for instance, the neural network PDF group, NNPDF, do something sort of similar up to this prefactor, but then ultimately fit just some neural network as the parameterization for the PDFs. And the idea in that approach is it kind of represents the opposing end of the spectrum in the sense that you don't have this explicit parameterization and you in principle have a form that is more sort of directly data driven, which is a very intriguing and very important approach as well. So as I've just said, in fact, there really are sort of two main families of approaches. There's the one that at least is our default inside CTEQ, for instance, where again, you have an analytic parameterization. And the important point on that side is that if I want to actually understand the uncertainty, that is to say the shape of the likelihood function in the neighborhood of the global minimum, then I get at that information in sort of the Hessian eigenvector set technology. That's that approach. If you want to instead take sort of the neural network approach that I just mentioned, then instead the uncertainty is encoded in many Monte Carlo PDF replicas. And what I wish to note is that in fact, there is a way of actually converting from sort of one family to the other family. And what I also want to tell you, again, if you forget a lot of what I mentioned, sort of the subject of the uncertainty in the PDFs and these different approaches is, again, another frontier in terms of our sort of quest for greater precision in terms of the PDFs. So again, if you take this sort of CTEQ style approach, but really just in general, we have no knowledge of what the true underlying parameterization is. So in a fit like the CTEQ family, what is often done is one simply tries many different candidate fits. And so the green lines basically are literally just using different polynomial forms, varying the number of parameters that are actively fitted, varying various things to try to understand the extent to which there is, if you'd like, a model uncertainty, which is part of the contribution to the total uncertainty in the PDFs. And again, this gets rather tricky because there really are no data at either very high or very low X that actually tell you what's going on. So that ends up being a crucial problem in the sense that there is this parameterization dependence. And that's why we spend a lot of time, trying these different parametric forms and just pointing at one randomly off the page. For instance, for the anti-down PDF, you see that the different parametric forms just absolutely go wild. For instance, as I go to very high X, again, due to the lack of data. So if there is a sort of model uncertainty, it tends to show up exactly in these regions where you're essentially sort of extrapolating. Now, I mentioned this sort of parametric uncertainty as one source of error in the PDFs. There are others as well. Obviously, as many of you are experimentalists surely appreciate, I have just the experimental errors that basically inform the global fit themselves. There are also the theory errors that I mentioned. For instance, the fact that just this matching is complicated or that I have some sort of scale uncertainty that has to be controlled in some way. Another thing that I kind of mentioned is also the subject of methodology, the fact that there is some dependence in literally just how I do the fit, right? How exactly I choose to break up the PDFs or the details of codes that are used or the details of the theory that's carried out exactly. There's often no one known way of doing this. And so that might sound just silly to you, but it actually ends up being very, very non-trivial. My colleagues and I end up spending a great deal of time doing what we call benchmarking, of just taking your fit and my fit and really stress testing them and seeing where exactly disagreements arise, where things work and don't work. As a statistical interlude, I'm not going to go into this in great detail. This is actually specific to the Hessian PDFs, actually. But what we really do, of course, is we need some sort of likelihood function, which it is typically basically just your good old-fashioned chi-squared, of course. And we take a definition of chi-squared that tracks correlated systematic uncertainties via fitted nuisance parameters. And you can do many different things in the context of a Hessian fit, for instance. The idea, of course, is that when I do an analysis of this type, I find a global minimum parametrically for the likelihood function. And then what I do is I have a Hessian matrix, which is just a big matrix in the second order derivatives as I vary the underlying parameters. And I diagonalize that matrix to find now eigendirections. So in, for instance, order 30 parameter fit, I'll end up with 30 eigendirections. And then I can take sort of variations that saturate the growth in chi-squared in each of those eigendirections. And on that basis, end up with actually a central fit and then 2n additional eigensets, where n is the number of parameters that are actively fitted. And that's what's typically shown in plots like this, where these various colorful lines are basically the eigensets corresponding to each of the various fitted PDFs about the central fit. You can do interesting things once you have this at your disposal. You can look at correlations, for instance, from one PDF to another PDF, or you can look at parametric correlations between the PDFs and anything derived therefrom. It could be a cross-section that I would calculate on the basis of the PDFs, for instance, or anything for that matter. It could be the moments of the PDFs. And what that allows you to do in principle is it allows you to get at some understanding of, as I vary a particular, say, the gluon distribution, how exactly does that correspondingly influence maybe the Higgs production cross-section, as I'll describe in a little bit more detail tomorrow. This is for the Hessian sort of family. You can do very similar things for the Monte Carlo, again, looking at effects of correlations, where you would go from sort of fully correlated, and there's a geometric sort of interpretation for this, to fully anti-correlated. So for instance, in general, when I do a calculation, a Higgs production cross-section would be expected to be very closely correlated, for instance, with the gluon PDF. As I tend to raise the gluon PDF in some specific region, then I might correspondingly raise the Higgs production cross-section and so on. So these correlations carry actually instructive information. I can play this game and try to get some feeling for how the PDFs relate to phenomenological things that I might calculate on the basis of the theory I have, as well as the fitted PDFs. So for instance, in a correlation plot of this type, where I'm plotting a Hessian correlation between PDFs of defined flavor, and actually in this case, a W to Z boson production cross-section, then you could see that there's a very close relationship between the strange PDF, for instance, particularly at low X, and these types of cross-sections. Why would that be, by the way? Is that to be expected? Is this just astonishing? Does anybody have a guess? Anybody have a guess? The reason why is because W production is a charge current process, right? So depending on what I do for the strange, I have a flavor changing interaction where I might emit a W from a strange quark. So strange goes to charm, for instance. So depending on, how large my strange might be at low X, particularly at kinematics that are sensitive to W production, then I can get some observable effect. And that's realized in these types of correlations. Now, again, I showed this kind of plot. I realize you're not going to be able to see that very clearly on the screen. This is just a sort of duplicate carbon copy of what I showed a little bit earlier in the talk. But again, I want to impress upon you that we have many different, not just points of data, but data from different underlying processes. And what this is meant to show you is the fact that each of these different measurements, a lot of these are actually sort of DIS-like measurements. And then on the bottom block, things related, for instance, to LHC or Tevatron type processes, those tend to access different combinations in terms of the flavors of the PDFs and in different regions of X and so on. So it's it might seem trivial. Those of you, if you end up playing around with LHA PDF, it's like, okay, I read these out. And what actually really happens, of course, is I need theory. And in fact, at least in general, next to leading order theory for all of these different processes. And so they're all somehow eaten by the fit. And then I can, in principle, then get some sort of constraint to all these different PDF flavors. Why is it necessary to do that? You may well ask. Well, it's because actually the sensitivity of any set of data tends to somewhat identify with particular flavors or particular regions in terms of their X dependence of the PDFs. So for instance, if I think about the sensitivity, which is something like the poles of each of these data that I quantify according to some figure of merit, in this case for the ratio of the D to the U quark at relatively high X, you see that it's actually, you know, the colorful points are the ones that have particularly large sensitivity. Then you see that most of the data in the global set are sort of grayed away, they're grayed out. And the red ones are, for instance, the fixed target Drell-Yan data from E866. There's maybe some sort of neutrino measurements, for instance, or maybe data from older experiments before you and in fact I were born with names like BCDMS and even older. Then what you find is that it's usually just a subset of measurements that are particularly important. So sort of the data-driven polls tend to be dominated by a handful. You can actually score the various experiments in a global fit. This is just some sort of scoring scheme. But what I want to stress is that basically there's a kind of power law like fall off, basically, you know, where it's really just specific experiments that have kind of a leading contribution. That's not to say that the other experiments kind of as I go down the chain don't do anything. They might be sensitive to other combinations, for instance, or they may actually influence the result of the global fit in some way that's difficult to say a priori, but that is sort of the nature of things. I believe I've gone for about an hour, so I think I'll sort of stop there actually. I was going to get to sort of the nuclear PDFs, but I think I will talk about that tomorrow actually. So the conclusions for today, let me just very quickly say, the PDFs, they're important, whether you're a particle or a nuclear physicist, I would actually argue. They encapsulate a lot of what goes on in terms of non-perturbative QCD, and it's very, very hard to get them. I'll just leave it at that. And if any of you ever go into this field, you'll learn from first experience that that's the case. Because they're hard to obtain, we're constantly on the lookout for new information from experiments and so on. So it's very, very tricky to do this. Don't forget about us, I suppose, if, you know, whatever you go on in your career, because this really, you'll find, you know, no matter what you want to do, if you want to understand gluon saturation at the EIC, if you want to understand sensitivity to some sort of technicolor scenario at colliders, you'll end up running into the PDFs and thinking, this is really a challenge for us. So tomorrow, what I'll do is I'll make the connection a little bit firmer toward the Large Hadron Collider and say why exactly the EIC is actually relevant in this larger context. I'll talk a little bit more about the quest for still more universal global fits, and just give you a sense for those things. So thank you for your attention. If there are questions, I'm happy to take them.
Okay, yeah, we do have time for questions.
Yeah, so I've probably gone a little long, so my
No
apologies.
problem, we're flexible schedule.
Yeah,
Okay, so on slide 15,
15. Let's check it out.
so you talk about how the dynamics of gluons account for most of the mass of the visible universe.
Right.
This is a question that's vexed me for a long time here.
Vexes a lot of us too.
Yes, because gluons, my understanding is that gluons are force-carrying bosons, which are like photons, which are massless particles that travel at the speed of light.
Sure.
So how can massless particles give rise to all that mass?
That's a great question. Yeah, it seems sort of counterintuitive. You're right. I mean, you know, I can think of various ways of answering that question. I mean, the type of observable that we care about is actually some sort of effectively gravitational form factor that tells you about the mass. And you can think back to Einstein, right? Of course, you know, what is mass and what gravitates? Well, it's anything that has mass or energy for that matter. So strongly coupled fields of gluons, they're strong for a reason. They're very, very strongly interacting. And in fact, as I go down sort of into the strongly coupled regime, if I can put it that way, to sort of low momenta, then the strength of the gluon interaction is very great. And if you can think of it very roughly, there's a great deal of somehow energy that's contained in these non-perturbative interactions, and that gravitates, right? So that generates a mass. Another way of putting it is, and it's not probably really clear, but if I think of a quark propagator, this is, if you'd like, a sort of renormalized quark propagator in the QCD gap equation language. The first order, before I think about any of this nonsense, it just sort of looks like a bare quark propagator, right? It just looks like 1 on q squared minus a mass squared of the quark, for instance. And the mass could be something very small. It could be the mass, basically the current mass that appears in the QCD Lagrangian. It could be 0 for the sake of argument. No matter what you do, if you know about QCD, then in fact, then you can just go nuts, starting from this bare propagator, calculating, if you'd like, a sort of tower of additional graphs that are consistent, that are propagator-like, but that are now dressed by a gluon, and now dressed by a gluon with some sort of quark loop inside, and whatever the heck else you want, you can write it down. And it becomes a matter, if you want to solve for this thing, the physical quark propagator, then it becomes a matter of actually self-consistently solving this equation up to your knowledge of all of the various non-perturbative interactions that are in here. And then you could do this exercise. What you ultimately find is, if you leave a sort of mass-like parameter in the physical propagator, a mass function that's actually explicitly dependent on the momentum of the quark, then you find that all of these interactions essentially get renormalized into an effective mass. And that's actually the constituent mass of the quark. That's why, in the QCD Lagrangian, the mass of a U quark is sort of MeV scale, right? It's tiny, but in fact, the effective mass of a U quark inside the proton is in fact maybe 300 MeV or something. It's an appreciable fraction of the proton's total mass. So that's roughly kind of how it is.
Okay,
That makes sense. And if not, we can talk about it more in the discussion, of course.
all right.
It's an interesting point. Other questions? Anybody? Yeah.
I'm told that unless your model or theory is contained within CTEQ, it's irrelevant. And so
Say again, unless it's contained in CTEQ, it's irrelevant.
yeah, exactly.
I don't know what that means.
That if you have published work with your models of quark behavior and CTEQ does not have that in their code, that what you have done is irrelevant. That's a great reaction, but I guess
I have no idea. That's bizarre to hear, but I mean, so in general, like, you sort of got the whole point of the talk that in general, what I want to do is I want to parameterize things flexibly, but where it gets kind of tricky is if you want to map this approach onto some random model. That's kind of tricky. I mean, you could always play the game of saying, like, all right, I have a particular model, and then that might inform a particular parameterization that I'm then going to try to fit, for example. You could do that. I don't know if that's part of, I can't speculate about this, what you're getting at exactly, but
it was a senior person who told me that, but I think I've misunderstood the talk. So you don't take models from the literature and incorporate them in.
No, not typically. Not typically. I mean, there are examples where sort of special cases where that's sort of done, but I mean, in general, what we usually do is just fit some sort of flexible parameterization. It's not necessarily directly related to one specific model typically, but you can do that, and we have in special cases. I might say more about it tomorrow.
Okay.
Other questions? Yeah, please.
How do you estimate model uncertainty?
Yeah, that's a great question. I mean, ideally, what you'd like to do is more sophisticated than what I described here. I mean, model uncertainty means many different things. So I mean, to first order, you think I have some theoretical problem I'm trying to solve, and I have a model uncertainty, and in the context of the selected model, I have a parametric uncertainty. And you think of the latter as being this is absurdly untrue, but you think is being trivial. It's not, of course, but you think, okay, I use some sort of statistical technology to deduce that parametric uncertainty. What's the true model though? I don't know. You know, that was actually kind of the point of this slide. Nobody does really. So I mean, and model uncertainty itself is somewhat nebulous as an idea, but there are different ideas for how to approach this. I mean, the model uncertainty you could also think of maybe trying to approach in some sort of machine learning augmented way where you could try to, you know, envision an enlarged sort of theory space, not just of the parameters and the confines of one model, but where you'd actually undertake some sort of model selection process. But I think the best answer to your question, at least at the moment, is there's not like some universal and unambiguous way of saying what the model uncertainty is. I mean, what literally is done is like, let's take hundreds of different models and fit them all and see sort of how that resulting spread, in, you know, how it compares to, you know, a nominal uncertainty that we would extract. A point that your question reminds me of that maybe I should have mentioned more explicitly is a fit like this also has to deal with, you know, the notion of tensions in fitted data. So we end up using a statistical quantity that we call the tolerance to slightly enlarge in a way that's systematic and related to sort of the disagreements in available experiments. We enlarge the uncertainty. And the idea in this case is to say, well, okay, this spread in different fitted parameterizations essentially falls within an envelope of this tolerance defined uncertainty. That's what's done. That's just literally telling you how this is done in this case. How you would estimate it in other ways, there are many different ideas and approaches, and that it's great that you asked that because again, you know, I think of that as maybe being really a you know, if you're looking for ideas for a PhD dissertation or excellent work as a postdoc, like somebody who would make progress on that would very, you know, not just impact this and get a paper, you could potentially literally impact, you know, all of high energy physics, you know, and how we, you know, the errors that we quote on Higgs cross sections or whatever. So it's a crucial point. Yeah. Yeah, sure.
So I know the Hessian error model comes out of the underlying Gaussian assumption from the chi-square.
Yeah,
right.
Yeah.
So
exactly.
how nonlinear does my model have to be before the Hessian error is just nonsense?
Yeah, that's something that we're constantly revisiting. So there's a point where, you know, if you drift, you know, the Hessian assumption, first of all, can be seen, for instance, in, you know, how sort of quadratic effectively does the chi-squared profile behave? How much does it look like effectively some sort of hyperparaboloid in the neighborhood of the global minimum? That's something that can be empirically tested kind of on the fly. In principle, you can get into trouble though. So, I mean, there's no, you know, baked dyed in the wool answer that, you know, blah, blah, that's this, but in fact, yeah, that is something that we're always checking. So you don't want to drift too far. For example, if you get too far away from the global minimum, as you know, once you diagonalize things and shift, then you can actually see these deviations that kind of spoil the behavior in the Hessian language. So that is something that has to be controlled. I will point out that's not, you know, such issues are not uniquely a pitfall of the Hessian formalism. If you do Monte Carlo, then you can run into very similar problems where I have some very large multi-dimensional parameter space, and it becomes a valid question. How well have I actually sampled that? So, and it becomes in fact even a geometric question where imagine I have 100 parameters. So I'm in this huge 100-dimensional space, and typically a Monte Carlo set is released with 1,000 replicas. How well could 1,000 replicas actually encapsulate the behavior of the likelihood function in that large dimensionally of a space? Not that well, actually, not that well at all. So it's actually an analogous problem, and they're closely related. And in fact, as I mentioned, you can interconvert between the Hessian and Monte Carlo, and that actually is closely related to your question. Yeah, please.
May I ask something on slide 11?
Sure. Yes.
Yeah, I'm kind of looking at these, functions here.
You sure?
If you look at the plots for the strange gluon and U bar, you see that at low X, you have this large width.
Yeah, you mean just like you're referring, I guess, to this,
Yeah,
to the band?
yeah,
Yeah,
it kind of narrow.
yes, exactly. So,
Why do you plot them like that?
why does it behave this way, basically? Yeah, so I think, as I go to very high X, first of all, no, I mean, all of the PDFs partly, there are several ways of saying this. I mean, one, just physically, you have something akin to momentum conservation, where as I go to very high X, all of the PDFs must vanish, of course, at X equal to 1. And in general, they're vanishing with some polynomial dependence, kind of as I showed wherever I showed some of the different parameterizations. As I go away from that, however, now I get into the region where I'm actually fitting to available data. So a lot of the like, I don't know, LHC or other data, for instance, that might be sensitive to this stuff sort of live actually kind of in this ballpark, roughly, maybe 10 to the -4 to 0.1 or so. And it's just, you have, first of all, I mean, it's very, very tricky, as I tried to say in words. I mean, notice maybe it's not as clear on this logarithmic plot, but I think you can still kind of see, I mean, the strange in green, for instance, and then the light quark, which is to say the SU2 PDFs, they all kind of collide. So having data that allow you to actually do, as we say, the flavor separation is not easy. And so that's part of it. That has a role in effectively sort of inflating the various uncertainties. Strange is somehow very difficult to access. And maybe we can talk about that in discussion. That's particularly tricky somehow, it turns out. But yeah, I would argue that that's kind of the main idea. You're sort of in this region where data are hard to come by, and you're also in the region where, the parameterization is actually really non-trivial. It's not just sort of quickly vanishing, going down to 0. I mean, the relative size of these uncertainties is, it looks like, oh, this is known exactly. I probably should, maybe tomorrow I'll show some of this. I mean, if you actually show the fractional size of the uncertainty as a function of X, actually the uncertainties blow up as you go to X of 1, but they are sort of suppressed on this scale. So I think when you plot in this fashion, they're simply more evident, if that kind of answers your question. Yeah.
Over at X equals 1, it seems like there should be a non-zero probability for an up quark have all the momentum of its home nucleon. Tiny, but non-zero. Is that included in there?
That should be a good discussion for any problem. So maybe that's something for tonight. No, it should vanish exactly. Yeah, just for momentum conservation reasons. You can also think of it in terms of relations to form factors as well. So yeah, maybe that's something to discuss. Other questions?
Yeah, if not, we'll have a chance this evening during discussion. So let's go ahead and break now for half an hour. We'll start at 1/4 after.